then I can give maybe more of a quicker introduction, but again, feel free to like pry about details and stuff. So there's sort of two ways that I like to motivate the p-adic numbers. One, I could maybe try my hand at afterwards if someone's interested, but I prefer to do this when I've reviewed a couple examples that I have ready to bust out. But I think there is a way. There's a nice way of motivating them, and we will come back to this in some form or the other, of trying to solve polynomials, right? So imagine we had an integer polynomial. Maybe I'm just going to end up telling you this explanation anyways. But so suppose we had an integer polynomial. So certainly if that polynomial had a root in the integers, right? So if there was some integer a such that that polynomial was 0, well, then certainly there would have to be solutions to this mod n for every n, right? So that's like one way that you could check. If you picked some n and you showed that that polynomial mod n had no solutions, well, then it couldn't possibly have any solutions in the integers, right? So that's a way to rule out the existence of solutions. But what if you wanted to go the other way, right? What if you said, okay, suppose I could solve this integer polynomial mod n for every n. Can I always go back and construct from that just a regular integer solution to that? Well, one thing we might try. So I'm assuming, and stop me if you haven't. I'm assuming since people have seen have generally seen things like the p-adic numbers before, you've probably heard of the Chinese remainder theorem, or perhaps we should call it Sun Tzu's theorem, because it can be attributed to a particular mathematician, not the guy who wrote The Art of War, though, where basically if we take its prime decomposition, right, it suffices to, if we're trying to solve this mod n, it suffices to solve this polynomial mod p to the I, well, at least for each of these exponents, right? So, well, the sort of easiest case of that is you might think, oh, well, when e equals 1, right? So we might start with the most humble thing and just ask, okay, can we at least solve this polynomial mod p for all, fix some prime p. And then, I mean, if you want to get a higher power, you might say, okay, if I had a solution mod p, could I then lift that to a solution mod p squared? And if I could do that mod p squared, could I sort of do this in steps? Could I start, so our sort of big lofty goal is solve this mod n for all n and hopefully get back to an integer solution, but sort of thinking, thinking in what's the word, reductive terms. We say, okay, I can reduce it to prime powers, and maybe I can reduce it to primes. So it turns out that there's a powerful tool for this, and that is what's called Hensel's lemma. So Hensel's lemma, okay, it looks like I'm just going into motivation 1 for the p-adic numbers, even though I feel somewhat unprepared. Normally, I like to give examples. If you want, we can, you can bug me for an example, and maybe we'll just ask Google or something, because I don't have any on hand, and I don't want to feed you lies. But Hensel's lemma basically says, if your polynomial, so if you have a root, so R is a root of your polynomial mod p, and if the derivative of your polynomial is non-zero mod p, then we can construct, then there exists some s such that fr is, fs is congruent to 0 mod p. mod p squared. So in other words, this gives us a way to lift roots. So if you can solve your polynomial mod p, you can solve it mod p squared. And in fact, this process can be continued inductively. And so you can actually find different values to solve it mod any power. Have I lost anyone?
Sorry, just remind me real quick. Are we looking only for integer solutions, or are we looking for just any?
We're only looking for integer solutions at the moment. Yeah. So yeah, taking mod makes sense everywhere here. Yeah. Okay. So the point that I want to get at, so normally Hensel's lemma, I'd like to stop and give some examples, but the point that I want to get at here is it actually is, so it's not just an existence thing. It's a constructive theorem, in the sense it tells you explicitly how to build this S. And in fact, the way that you build it is you take your R, and it tells you exactly how to choose a number S, which is between, well, maybe I'll call it S1, which is between 0 and p minus 1, such that you write the number as R plus SP, R plus S1 P1. And so you can see the point is that this, whatever this S is that you get, this S1 that becomes a root mod P squared, the point is when you reduce mod P, you recover the root that you started with. And in a similar way, once you want to go up and say build a root mod 3, the root mod 3, again, it's going to start off with R and S1 P to the 1. And again, it's going to tell you explicitly how to choose some S2 between 0 and P minus 1, such that this term is going to be your root. And so again, you can see that if you looked at this mod P squared, you would in fact recover your root mod P. And if you looked at it mod P, you would recover, you would recover the root mod P squared. And if you looked at mod P, you'd recover the root mod P. Is this making some sense, or is there anyone I've totally lost with this because it may be a little abstract?
I mean, I'm taking you mostly on faith, but I think I get the claim.
I have one question.
Yeah.
So going from R having multiplicity 1 guarantees that S also does. Is that correct?
Yes.
Okay.
Yes. I believe, yeah, it just comes down to the multiplicity of R. Yes. Yeah. Fact check me on that. But yeah, I think it just comes down to the multiplicity of R.
Okay. So
Yeah.
wherever you start with multiplicity 1, you can just keep going up powers. You don't need some additional check,
Right. Yes,
presumably.
exactly.
Okay, cool.
Exactly. There might be some power maybe one has to put here or something. Yeah, there's definitely one should fact check me on this, because I'm sure there's some small part I'm missing out that have dropped here in my assumptions. But yeah, this is 80% correct at least. So the thing is, assuming these conditions are satisfied, we can keep playing this game forever. And so something interesting happens, right? Because, well, you would want to say, okay, if this is going to actually converge to an integer, I mean, one thing that you would want to be the case, and so maybe I'm just going to rewrite the notation a little bit. So what I was calling R, I'll call A, A0, I'll call S1, A1, A2. So if you kept playing this game, right, you basically took what is more or less this base P expansion, right? You could keep playing it, Now, if it is going to yield you an honest-to-God integer at the end of the day, then you should expect that after there exists some n, such that after which all of the coefficients you choose will be 0, right? The coefficients of the higher powers will be 0. Because then then you would get an honest to God integer, right? And that honest to God integer, just this finite part here, would be a solution mod p to the e for all e. The problem, though, is in practice, one does not always get, it does not always die after some finite number of steps. It turns out, in general, it will continue on forever. And so now we have this interesting thing, because it's like, well, if you literally interpret this sum, it diverges, right? You're adding up increasing powers of p. This is a divergent sum. So this is like, it's tempting to just dismiss it as this meaningless quantity. On the other hand, it is somehow storing some information, right? Because you could just imagine instead storing a vector of information, right? Where in the first component, you put the solution mod p. In the second component, you put the solution mod p to the 1. In the third component, or sorry, I guess I should say in the 0th component, we put the solution, what am I saying? Sorry. Yeah, in the first component, I'm getting, yeah, the index is slightly different, is shifted one from the powers, but I think hopefully I'm getting the idea across, is that in each component you just store the solution. So this is the solution mod. This will be a solution mod 3, I guess, and this is the solution mod, or p to the 3, solution mod p to the 2, and this is solution mod p. Sorry, was there a question?
No.
Okay. So what we do is we store everything then in this giant vector of data, basically. And what's going on in this? So it's some tuple of numbers. Well, what we can really view it as, it's a choice. Really, it's a choice of element in this product zp minus zp squared, or sorry, times zp squared times zp3 times zp4, and so on, etc. Right? Really, we're just describing an element of this, right? Because this is going to be some number between 0 and p to the 3. This is some number between 0 and p squared, and this is some number between 0 and p. And so we can interpret all of these as just different numbers mod p to different powers. There's one other thing, though. So it might be tempted, you might be tempted, because I'm heading towards the p-adics, right, to think, oh, maybe the p-adics are just this whole infinite product. We just take the product of all of these. But there's one other very important property going on here, and that's the fact that, remember, if I look at this component modulo 2, I simply recover the next one, right? I recover the entry that came before. And similarly, if I looked at this entry, mod p, I would recover the first entry. And in fact, this is transitive, right? If I look at this, again, the mod 3 entry, and I just took in one step, computed that mod p, again, I would just recover a naught, the zp entry. So here is definition number 1 of many of the p-adic integers. So the p-adic integers, z subscript p, of course, not to be confused with modulo p. This is the collection of all elements of the product over the integers mod p to the n, over the integers mod p to the n, subject to the condition that if you applied the, so this is maybe a little bit so if you take the projection map, so by the projection map from M to K of AM, I just mean the map that goes from the integers mod p to the m to the integers mod p to the k, that simply sends an element and reduces it mod pk. I'm assuming here that k is less than or equal to m. And so we demand that these maps are compatible. So for any m and n bigger than k, those entries, the m and n entries, both project down to the same kth entry. Okay, maybe that seems a little fancy and weird. All it is just trying to capture this idea that we saw, where if I took my entry in the mod 3 case, I simply, the fact that if I reduce it mod p, then I recovered the same thing as the entry in the mod p slot. Does that make some sense? Hopefully,
let me try to regurgitate that back to you. I think I get the reason why we're doing what we're doing here, but I want to make sure. So like, my understanding is, this set that you've constructed here with like a0 plus a1p plus a2p squared is we're sort of converging towards something in some sense, insofar as more and more data is being stored as you get further and further to the right. And so the goal is to basically just store that last element, but we can't just store the last element, so we store the whole set, and the set is defined by how it gets well, each time you add more information, that's sort of adding more data to what you're storing as the thing that you care about.
Yes.
And you're just, in that projection map, you're just capturing the relationship that everything has to have with the other elements in the set.
Yes. Yes. Yeah.
Cool.
Yeah,
that makes
sense.
So
in some sense, yeah. And where did this come from? Like, it came from, our attempt was trying to solve polynomials mod p. And we realized that from Hensel's lemma, we were able to sort of lift, if you had a solution mod p, under certain conditions, you could lift it to mod p to the n. And under certain conditions, you can do that indefinitely. And while the literally interpreted series is nonsense, definitely there's some need for us to store that data. And so it makes sense for us to try and talk about the collection of all those pieces of data. So in some sense, you can think about the p-adic integers as a sort of natural place where families of solutions to polynomials mod p, mod prime powers should live. It's sort of a natural space where you can store families of solutions to polynomial equations.
I have another question. If you could scroll up just a little, to where we had. Okay, so there we have, so these coefficients, this a0, a1, and a2, by like the way powers work, all these coefficients are from 0 to p, or 0 to p minus 1, right?
Yes, exactly. Yes.
So instead of special sequences of elements in z mod p to the n where the reduction functions work out nicely, could we merely take like 0 to p minus 1, that's like z mod p. Could we just take like an infinite product of z mod p's and do the same thing, or no?
Yes, so that's exactly what I mean. That's exactly the sort of alternative description I was getting towards here. So
with that, you have a z mod p to the n, and clearly that's too much possibilities, because you don't want every p squared slot.
I see what you're saying.
I'm just saying the coefficients.
Right. Yeah, I suppose it would be possible. To do such a thing.
It might be harder to do operations.
Yeah, I was about to say something like that.
Yeah, I mean, that's exactly the truth. Although I don't know how to motivate it at this point in the story, right? Because so far I've just sold you the story about, oh, solutions mod P. It's like, well, why would we want to do operations on it? You could say, well, why wouldn't we want to do operations on it, right? We love doing operations on things. But yeah, that's I think part of the explanation. Yeah, yeah.
Okay, thanks.
Yeah, yeah. Okay, so this is definition, yeah, this is maybe definition one of the p-adic integers. Where would, so the fact that these are integers maybe naturally suggests, I mean, one way, I don't know how much, I don't know how much, general algebra people have seen, but I mean, even if you don't know, how to take the fraction field of a PID in general, you probably at least have some intuitive sense, even though you may not know the formal definition of what a fraction field is. You probably already have some intuitive sense, as if I told you, oh, the field of rational numbers is the fraction field of the ring integers, right? Because what do we do? I mean, we just sort of formally invert the non-zero integers, and we can just kind of create these symbols and define these like multiplication and addition rules. Well, it turns out that this generalizes, and it generalizes in such a way that includes the p-adic integers. So you should really think of them as kind of, well, there's a lot of ways in which they're spiritually analogous to the integers, and there's a lot of ways in which they're very, very different. But one way in which they're the same is we also get a field which we call the fraction field of the p-adic integers. Oh, mind you, this doesn't make a ton of sense until I've told you about the ring operations on this. But okay, so maybe I should say what the ring operations are, since this point about the operations just came up. Yeah, so looking at this big infinite product, you might think, well, these are all, this is a product of rings. Is this still a ring under component-wise addition and multiplication? And yes, it is. I mean, the only thing you need to check is that if you did take a product or you added two elements of the ring, you wouldn't end up getting something that fails this condition. So it's definitely something to check here. But the point is that you do get a ring at the end of the day. So much in the same way that the integers are a ring, and you can form these sort of formal fractions, the p-adic integers also form a ring. And definition number one of the p-adic of the full p-adic field QP is as the fraction field of this. Okay. So my plan now is to sort of do a total non sequitur and talk about now my other favorite way of introducing the p-adic numbers, and talk, which will involve one of my favorite theorems in mathematics, and then hopefully wrap them all back up together in a really nice application of the p-adic numbers. That'll maybe help people who said that they've seen these before, but maybe aren't so sure what you do with them. So before I sort of switch gears, are there any lingering questions about this first pass at the p-adic numbers?
I have a question.
Yeah.
So there's like just the raw product without that condition.
Yeah.
It seems like this is a subring. Is there anything interesting to say about like the factor ring of that over the p-adic?
Oh. I've never
I have
thought
no
about.
idea what that would look like, but
Yeah. Yeah. I've never thought about that actually, but yeah, maybe I'll have to think about that. I don't know. I don't know.
okay. Just curious
Yeah.
if that was like a commonly studied thing that you would have something to say about, but okay.
Right. No, not that I've seen. Not that I've seen.
Okay.
But yeah. Yeah. Um Maybe one last thing I'll just say on this actually before I move over though, is that technically what I've just explained to you here. So I don't know how. Also, maybe there's people who don't know a ton of category theory. Maybe it scares you or something. But you've secretly just understood the concept of a limit. because I've without giving you the proper definition of a limit, I've also just essentially explained to you one of the definitions of the p-adic numbers that sometimes people give is as this inverse limit of the integers mod p. And more or less, when you unpack all of those definitions, you get exactly this subring. Okay, but let's now jumping over to a totally new, maybe not totally new perspective, but another perspective I like to think about when it comes to the p-adic numbers. So one thing, of course, that's been really useful for us is the real numbers and the ability to do calculus, in particular integration theory on the real numbers. Truly a blessing. But one of the ways that we construct the real numbers, of course, there's Dedekind cuts, but the way that I prefer, and you'll see why in a second, is to first consider the rational numbers as just as a metric space with respect to the absolute value, or rather, I should say the metric given by the absolute value, right? Distance between two rational numbers is just defined to be the difference of the absolute value of their difference. And the real numbers can then, and for reasons that maybe I'll talk about towards the end, but for now, I'll leave it mysterious because it's kind of high level. But for some reason, I'm going to index the ordinary Euclidean absolute value with a little lemniscate and infinity. We sometimes call it the prime at infinity. This will sort of be explained in a moment, but I'm hoping you can just accept this for now. One way of defining the real numbers is we take the rational numbers and we take the Cauchy sequence completion. So we define, in general, if you have a metric space, what you can do is take the Cauchy sequence completion, where you define X to basically be the set of Cauchy sequences, in elements of X modulo some notion of equivalence. Is this totally foreign to people, or are people like vaguely familiar with Cauchy sequence completions?
Maybe I'm wrong, but aren't we just saying like the set of things that it could like that limit points could be?
Yeah. Although it's this sort of weird thing where like it's very tempting. It's very tempting with the way that we normally think about sums and sizes in the rational numbers, and it's very tempting to look at this sequence and say, oh well, clearly it's like converging to something, right? And in some sense it is. Of course, like people were working with pi intuitively well before we had the notion of Cauchy sequences. But if we're sort of thinking about this from the perspective of foundations of mathematics, where we're imagining we're trying to build everything up in layers, right? From set, we start with the natural numbers, then we define the integers, and you could define that as some sort of like a pair of a pairs where it's a natural number in the first coordinate and a 1 or 0 in the second coordinate, which is supposed to tell you whether it's positive or negative, right? And then you build up the rational numbers, and those are again just sort of formal pairs of natural numbers. But then we have this equivalence relation, where like the pair, so the pair AB, is supposed to represent like the rational number CD, and the rational number A over B, and the pair CD is supposed to represent the rational number C over D. Then we say that these are equivalent if AD minus BC is equal to 0, right? Because you would exactly get that from this if those fractions were equal, right? So we build it up in these pairs, but we have to give this sort of rigorous definition of what it is first. So in the same way, you're totally right. like you look at rational numbers, you look at this sequence with our notion of size, and you're like, well, it seems like it's converging to something that just has this infinitely long string of digits, and it's very tempting to call this a number because I can do all this stuff and it behaves like a number. But on some formal level, I need to construct it. And so how am I going to construct that space? Well, instead, again, I can't just like magically fill it in with this point. So what I'm going to do is I'm going to take the sequence itself that I think is, should be treated as a convergent thing, and I'm going to define that to be a point. I'm literally going to define, my real numbers to be sequences. And so when, if you take the Cauchy sequence definition completion of the real numbers, when you write down pi, what you're secretly writing down is an equivalence class of Cauchy sequences of rational numbers, which are all equivalent to this particular sequence of rational numbers.
How do we measure equivalence? Is it like
so that's a good thing. And actually, I maybe in this case I should have maybe added the assumption that it's a field. So
can I take a stab at that? I think maybe you would do it by first of all just defining the operators merely just piecewise in terms of the component, like lining up the elements of the sequence one by one, and that way you can like define addition and subtraction, because like if you have two Cauchy sequence, you could add the two of them up by just adding them element by element and figuring out what that converges to, and then you could just define convergence, or sorry, define equivalence in terms of you just subtract them from each other and you get 0.
Yes, exactly. That's exactly it. That's exactly it.
Just to be clear, when you say get 0, we mean get
something
a sequence
that
converges to 0.
Yes.
Right. Yeah.
Yes. And that's the beauty of it, because when you talk about a convergence of rational numbers converging to a sequence of rational numbers converging to 0, you can do that purely using the rational numbers, right? Like your epsilon and deltas in that definition can all be rational numbers. So that's sort of the brilliance of this construction, is that if you're thinking about it as like a bottom-up approach of how we build the real numbers out of this, you can that's sort of this clever idea. Yeah. So, but one of the things that's going on here, right? So I mentioned that we like to talk about metric spaces in general, and why do we do that? Well, we realize that yes, there's the standard way of defining distance is arguably the most useful in our real world, but there's a lot of other different kinds of distance functions that we might want, right? And the whole reason why we have the abstract definition of a metric is to say, well, let's actually study the properties of what it means to measure a distance between two things in a greater generality. And so thinking about that with the real number, or sorry, with the rational numbers, what we could also take is look at different kinds of absolute values. So we might ask, what are all the norms that I could possibly have on the rational numbers? So what do I mean by that? Well, much like a metric, I want my norm to be greater than or equal to 0. So I guess let's take it as a function from the rationals. Now I'm going to let it, I could say into the rationals, but I'm going to let it go into the reals. But it looks like there was a message that was maybe interesting about an alternative something. Maybe I'll look at that after. So a norm from the rational numbers to the reals. So we want it to be non-negative, and we want it to be 0 if and only if x is 0. We want it to obey the triangle inequality. Normally we put that one last. So I don't know why I put it as number 2. And we'd like it to be multiplicative. So AX will be the norm of A times the norm of X. And so we can ask, well, are there other interesting norms on the rational numbers that we haven't considered here? Since addition comes before multiplication, yes, exactly. Yeah. Yeah. So it turns out that the answer is yes. And in fact, one of my favorite theorems in mathematics is a complete classification up to topology of what all the possible choices for norm are. So the other norm, some of you may have guessed it already, is the p-adic norm. So how is that defined? First, let me tell you how it's defined on integers. So take an integer n. So we get one of these norms for each p. Take an integer n. The p-adic norm is going to be obtained by first you factor out from n the largest power of p that appears. So n is equal to n prime times p to the r, where now n prime is some integer which is relatively prime to p. And the p-adic norm will be defined to be p to the minus r. So in other words, we're thinking of integers that are very, very divisible by p are very, very, very small. More generally, if we have, let's say, a rational number, the p-adic norm will be defined, well, we take a very similar sort of process. So we factor out the largest power you can from A, and you factor out the largest power you can from B, and you define the p-adic norm of this element to be p to the s minus r. So rational numbers that have maybe I'll give you an example, right? So the 2-adic norm of 12, well, we factor that as 3 times 2 to the 2. So the 2-adic norm of 12 is 1 over 4. Meanwhile, the 5-adic norm of 12, well, that doesn't have any factors of 5, so that's just 1. But something like 3 over 7, its 7-adic norm would actually be 7. So that's kind of, if you've got a lot of primes in your denominator, then you're going to be pretty big. And in the same way that we took before the Cauchy sequence completion of the rational numbers with respect, like one way of defining the real numbers was just taking the Cauchy sequence completion of the rationals with respect to the Euclidean absolute value. You might also try and take the Cauchy sequence completion of the rationals with respect to the p-adic absolute value and see what you get. And this is exactly definition number 2 of the p-adic numbers is exactly that. You take the rational numbers and the Cauchy sequence completion with respect to the p-adic norm. And here is my now favorite. Sorry?
Sorry. So this is because now the big powers of the primes are considered very small, so adding them doesn't change the norm as very much. Actually, it doesn't change it at all.
Sorry, I'm not sure what you mean.
Like in the process where you were going from like R to S1 plus the first power.
Oh, yes. 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 Yes.
Okay.
Right. Yes. And in fact, okay, there's something really interesting to say there. We'll come to it in a minute.
Okay,
But yes,
cool.
that's a very important observation. That's a very important observation, and I'll come back to that in just a second here. So let me first just tell you my one of my favorite theorems, and I should add, by the way, so one thing that I don't know how much time people have and to listen to me yap. I don't know how much I'll want to yap after 7. Maybe go 2 hours. I don't know. But there is a generalization of this to number fields. So finite extensions. So all of these things I'm saying actually have extensions and are very useful in algebraic number theory more generally. But the sort of basic version of what's called Ostrowski's theorem says the following: if the absolute value, so if we have a norm on the rational numbers, then if it's not the trivial norm, then the topological, so the rational numbers viewed as a topological space, so by which I mean you look at the corresponding metric and you view this as a topological space, is homeomorphic, so equivalent in the topological sense, homeomorphic to exactly one of either the real numbers or I was about to say, sorry, is this is all happening on the rational numbers, is homeomorphic to exactly one of q with the Euclidean absolute value or q with one of the p-adic absolute values.
And just to be clear, all the p-adic absolute values give you different topological spaces?
Yes. So for any two, for P and L distinct, the topological spaces are not homeomorphic for the corresponding L and L-adic and p-adic metrics. So it's tempting. You might think, oh, the p-adic numbers, you somehow want to group them together in your mind, but they're worlds apart. They're somehow very distinct. Maybe to say something, I don't know, seemingly unhinged, just this connects a little bit to my research. For example, if you're studying the representations of like algebraic groups valued in the p-adic numbers, and okay, normally you do things infinite dimensional, but say we're studying representation, which means it's valued in matrices over GL with L not equal to P. Basically, the theories are identical for looking at the representation theory here. And P, by the way, in this case, could also be, like infinity or something, like it could be the real numbers. Just because the topologies are so incomparable that like you might, if you're familiar with like Lie theory stuff, you might want like smooth or like, these are topological spaces. So you might want to look at like continuous maps or something. And so somehow it's all sort of uniform if L is not equal to P. But then suddenly, if you change that and you make the p's equal, now there's all of this very complicated stuff. I mean, I'm generally ignorant of taking L equal to P because there's a whole extra different level of sophistication and stuff. Because now you have compatible topologies that talk to each other, and it's weird. It's weird. But okay, that's jumping way ahead. But this is my favorite theorem because it is this beautiful classification. It's this topological question, right? Up to topological equivalence. What are the possible norms, the possible absolute values I could put on the rational numbers? And the answer is this arithmetic thing, right? It's classified by the prime numbers and this one other thing. And I just think this is fantastic. And so somehow there's a very real sense in which I don't know, there's this the rational numbers sort of gives rise to each one of these distinct kind of fields. And one of the advantages of this, maybe I'll talk about this depending on time, we'll see. But one of the useful things I do want to say a bit, at least maybe before 7, I'll make sure I say something about it for the people who are interested and maybe want to go by then, is that one of the sort of important applications in number theory is the idea of a local global principle. So this appears, throughout geometry and number theory. And the idea is, we would like to understand things about the rational numbers, rational solutions to elliptic curves. We want to study, like Galois theory, finite extensions of the rational numbers. And the idea is, well, perhaps since there's this intimate relation between all of these fields and the rational numbers, maybe there's some way to transport information back and forth. So I mean, for instance, a rational number, every rational number, like the rationals embed into each one of these fields. So a rational number will determine a bunch of p-adic numbers, but much in the same way, going all the way back to our old exposition, right? When we had like some sort of compatible family, right? We stumbled upon like compatible families of integers mod p to the n. One might wonder, in the same way, is it possible to pass information back and forth between somehow like compatible families across all of these different completions? And sort of a big punchline of this is what's it called? The Hasse principle. And what this theorem says is given a quadratic form. So this is a polynomial with rational coefficients in finitely many variables, but it's quadratic, right? So it's gonna look something like a x1 squared plus b x1 times x2 plus c x3 squared plus d x4 squared, or something like this. And maybe let's put one other cross term, like x1 times x4. And one of the sort of big useful things about the p-adic numbers is this famous theorem that says there exists a solution. So there exists a rational solution to the equation f at, I'll write it x vector notation, right? Because we're plugging in a tuple of rational numbers, equal to 0, if and only if there is a solution in every p-adic field. And here we're allowing p to be infinity, i.e. the real numbers. So why is this such an advantage? Well, think about it. I mean, we're solving things like quadratics, right? You're going to want to be taking like square roots and stuff. That's something that's simply not allowed in the rational numbers. But definitely that's something that we can do. Okay, we can't take it of negative numbers. We can't take roots of negatives in the reals, but certainly a lot of numbers we can take roots of in the reals. In the same way, it turns out this is also the case for the p-adic numbers, right? Because it's this analytically complete field. Just like in the real numbers, all the Cauchy sequences converge. That's also true for the p-adic numbers. And so you have just access to way more numbers. And so this gives us a situation where normally, like, you want to try and find solutions for some quadratic form. Well, how do you do it? There's maybe a couple primes, I don't know, pick some primes at random. there's like a couple primes that maybe you have to work with or something a bit technical, but then usually the arguments work out so that for the rest of this infinite family of primes, you can sort of play a very similar game. Like the argument will work the same in each of these p-adic fields, and you can check a solution in the real numbers. Now it becomes much easier to find rational solutions. So this is one instance of what people call a local global principle, and this is one of the one sort of interesting application, if you will, of the p-adic numbers and the real numbers, is that it gives you this easier way to solve, for example, polynomial equations. And by the way, there's a whole bunch of stuff. This fails in general. However, a whole bunch of study, say in the field of elliptic curves, there's all of this stuff about like things about like Galois cohomology and these things called Selmer groups and whatnot. And essentially what these things help you measure is failures of the Hasse principle. So sometimes this can actually help you find rational points on elliptic curves by looking for rational points over these, again, analytically complete fields where, again, you're allowed way more operations. So finding points for those fields is going to be much easier. Yeah, okay. So that's a bit of a pitch as to some of the usefulness of p-adic numbers more generally. I see some people have to go, so maybe I'll stop here for questions and also to see if, I don't know, are there people who want to stick around a bit? Because I could talk more about, I could go more into more detail about like how this p-adic absolute value connects to like what we talked about with those, the series version of the p-adics, and also like some of the weird, there's weird topological properties to talk about. Yeah.
I have a question about that. The theorem classifying rationals.
Mm-hmm.
What does an open set look like in one of the p-adic?
Oh yeah, so this is a great question. They're crazy. They basically look like a fractal. Let me tell you one mind-blowing fact about the p-adics that is not going to help you at all picture them, well, you'll see. I'll talk about them. Actually, I can help draw you a picture for the three adics. I can help draw you a picture. But let me tell you this fact first. So given any, so take a point y in any epsilon ball around x in the p-adic numbers. Then the epsilon ball around centered at y is equal to the epsilon ball centered around x. So this means in the p-adic numbers, if you take an open ball, every point of the open ball is the center.
This just follows from discreteness of the metric, right?
Yes. So that's one of the other properties I hadn't talked about. Yes, but yeah. So you'll often hear you'll hear these described as non-Archimedean fields, or sometimes you'll see the term ultrametric fields. So the ordinary triangle inequality just says that x plus y has to be less than or equal to the absolute value of x plus y. What an ultrametric does is says, well, not only is that true, but the much stronger thing is it's less than or equal to the max of either one of these. And yeah.
Oh, just sort of a weird nitpicky question. So you said these are sometimes referred to as non-Archimedean fields.
Yes.
Like that's definitely a non-Archimedean metric.
Yes.
But like the definition of non-Archimedean field I'm familiar with doesn't make any reference to a norm. Are these equivalent and I didn't realize before? Or is that like, or do they call them non-Archimedean fields even though they mean like fields endowed with a non-Archimedean metric? Or like, does one a subset of the other?
Actually, that's a good, that's a good question. So non-Archimedean field should mean, you should think of it as a field equipped with a non-Archimedean metric. Now that may not always come through, because maybe you're dealing with purely algebraic properties of that field. But generally it being Archimedean or not is really a reference to the metric. There are other it would maybe be weird to call something like, there's like, function fields in over finite fields, and these are maybe also called non-Archimedean.
I mean, I can make it precise and then we just move on. But basically, like, a non-Archimedean field is often really big because it has like infinitesimals and more infinitesimals or whatever, and it's often so big that a real valued metric isn't gonna be reasonable to use.
Yeah, I'm not sure. I mean, so yeah. I'm not sure. But one thing I do want to explain, maybe just for people who don't know this, is why the term Archimedean and non-Archimedean. Well, Archimedes, being the big brain gigachad that he was, he realized that if you had a long stick and a small stick, but you put a bunch of small sticks of the same length, and if you put enough of those small sticks of the same length end to end, eventually they would overtake the big stick. Wow, ancient Greek philosophy. Those guys were bright. But it turns out, right? So this is sort of manifest in the fact that if you took, right, n, the absolute value of n times x in the real numbers, I mean, this is going to be, right, this is going to be n times x. So eventually, like, if you take n sufficiently large, like this will be bigger. Well, you could just take n to be 2, and this will be bigger than the absolute value of x. But now this fails, right? Or actually, I should say, if we're trying to compare it to, so we're imagining the stick length here is like absolute value of x, and the stick length here is the absolute value of some y. So if you choose n sufficiently large, you can make this happen, right? And this is, you go read Rudin, right? This is like what he calls the Archimedean property. But now this fails, right? This fails in non-Archimedean land because, n times x in non-Archimedean land is just x plus x plus x dot 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 plus x n times, but that is bounded by the maximum of the absolute value of x and the absolute value of x and dot dot dot, which of course is bounded above by the absolute value of x. So somehow you put p-adic sticks together and they don't get any longer. Another way in which the p-adic numbers are very strange. Yeah. Any other questions?
I had one. Go ahead.
I was just going to say, you mentioned before there are like counterexamples to the Hasse principle, or Hasse principle, I guess, and like there's a pretty simple one. I don't know if you had it or wanted it.
Yes. What is it? I'm just gonna look it up so I can write it down correctly. There's this one famous one.
So it's 3, 4, 5 in cubics.
Right. Is there's coefficients out in front?
No, the coefficients are 3, 4, 5. Like 3x,
and it's
3x
cubic.
cubed.
I see. Right. Yes. Right. Yes. Yeah. And who's it due to? It's some famous person, right? There's some name to it. Sorry?
It's Selmer's.
Selmer. Oh, right. Of course. Yeah, Selmer. Of course. Yeah. Yeah.
What does this mean?
Sorry, what are we looking at?
I don't follow.
What is this? Yeah. Jinx.
So up above I mentioned that there's this Hasse principle. So right when we it's a theorem, at least for quadratic forms over the rational numbers. So if you have quadratics over the rational numbers, then you can have there's a solution to that quadratic form, right? A tuple that makes it equal to 0, if and only if there's a solution in each of the p-adic numbers, including the reals. I mean, one direction of this is simple, right? Because if there's a rational solution, of course there's a solution in all of these fields because all of these fields contain the rational numbers. The more significant thing is going the other way, right? If you knew you had a solution in all of these fields, then this guarantees you can glue that together into a solution over the rationals. However, there's this very famous counterexample by Selmer. So notice this is not a quadratic form, but it turns out that this curve has, or surface, I guess I should call it, has solutions in QP for all P, yet no rational solutions. So sadly, it's a counterexample to it working in general. But not all hope is lost. There is, like I mentioned, there's these, so also named after Selmer, there's these things called Selmer groups, which are attached to the study of elliptic curves, for example. So again, this will fail in general for an elliptic curve, but there's certain elliptic curves for which it doesn't fail, and in some sense, you can like understand the extent to which this principle fails. Yeah.
I had a question closer to the beginning. Why do we take the fraction field of the p-adic integers in the first place?
Yeah, that's a good question. I'm not sure I have a great motivation. I have a great motivation for it. I mean, so one thing I didn't quite explain. I mean, we talked about it a bit. Was the fact that this thing has the structure of a ring, right? Well, certainly, multiplying together all of the integers mod prime powers, this has the structure of a ring. And then it's a theorem you need to check that looking at this sort of subset, that this is in fact a sub ring. And yeah, there's not necessarily maybe a deep motivating reason for why you would study this. But it is in particular, I think I misspoke earlier. I said p-adic, but what you can really take the fraction fields of most generally are integral domains. And so if you have an integral domain, you can form a field out of its fractions. I mean, in some sense, it's just like let's say we were trying to work with the p-adic integers. We're trying to find solutions for them. Again, it's just another layer of flexibility, right? It's like, okay, let's work in the rational numbers. Like this is a sort of thing that happens a lot. Like for instance, in the study of Pythagorean triples, like I don't know if you've ever seen the classification of all Pythagorean triples, right? But what one does, so you're trying to find all integer solutions, a squared plus b squared equals c squared. What one does is dips into the integers or sorry, into the rational numbers for a moment and says, okay, well, what if we divided through by c, and then we're looking at, we're looking basically at points on a circle. And now we can leverage some sort of geometric intuition to try and come up with a classification for all the rational points on here. And each of those rational points should correspond to honest to God integer solutions, right? So it's a strategy of like, we really care about integer solutions. Well, we allow ourselves this flexibility to dip into the rationals if we need, and then see if we can come back. So you could imagine it in the same way, like we are trying to solve some sort of equations. We are trying to solve them mod p, that forces us into mod the p-adics. And then you could say in the same way, well, now maybe we're working with some sort of equations over the p-adic integers. Really, I care about solutions there, but why don't I, do something like go into its fraction field so I could do something more flexible like this? I mean, this is exactly something you could do. Is maybe you ask this question about, what do solutions to this equation look like over the p-adic numbers? And you might guess, based on your knowledge of how to do this for rational numbers, you might say, oh, well, why don't I go over to QP for a second, think about, what this would be in some sort of geometric sense, and see if I can, recover my integer solutions from that. I don't know if that's, yeah.
Is there a simple counterexample for why they're not a field themselves?
Yes. So the invertible elements. Let's see. Am I going to get this right? So, basically, they just it's the same reason, in a sense, why the integers aren't a field, because not all p-adic integers are invertible. So. What's an example? I think if you start with anything whose so every p-adic number, right, has a base p expansion. Every p-adic integer, well, every p-adic number. This was something else I was going to talk about, but I believe that basically whenever a is not equal. Whenever a is equal to 0, rather, then the element is not invertible.
Okay, that makes sense.
Yeah. So in particular, to give you an explicit example, then I guess 3 has no inverse in the 3-adics. Yeah. 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 So one thing that's maybe worth mentioning is also, why does this thing converge? Well, if we think about the sort of the nth partial sum of this, right? What's the p-adic absolute value of the nth partial sum? Or kth partial sum, I guess I'll call it. Well, this is bounded. I mean, this isn't strictly a proof of convergence, but actually, I'm gonna say something real crazy in a moment. This is bounded by the p-adic absolute value of each of these individual terms. And what are all these numbers? Like these are all small. They get smaller and smaller. The higher powers get smaller and smaller, right? This is p over k, right? P minus 1. This is this will just be 1. And in fact, what I've just shown you is that this is bounded above by 1. And so, in fact, actually what I've shown you is that the p-adic integers are contained in the ball of radius 1 around 0. And in fact, more is true. This isn't just a subset. This is an equality. And so here's a crazy thing. ZP, it's a ring which is compact and clopin in the p-adic numbers. Which I don't know. To me, this is it's crazy. How do you have a ring that's the unit ball of radius 1, but it's the closed ball, but it's also the open ball, but it's also a ring, but it's also compact? I mean, it's kind of mind bending when you first come across it, but it's also kind of beautiful. Oh, and let me say one more thing about this series. So here's sort of why analysis is superior in the p-adic numbers, or maybe one reason. So, probably in everyone's Calc 2 course or whatever, you spend at least a month learning about all of these tricks. Like, life is basically hard because a series converging implies that the limit of the nth term goes to 0. But the whole reason why we spend 2 months on it is because the converse fails miserably. But this is no longer true in p-adic land. In p-adic land, a series converges if and only if the limit of the nth term goes to 0. Another beautiful fact I love about probably we've all encountered crackpots and or just never mind crackpots. This is generally people being confused about the fact that 0.9 repeating is equal to 1, right? And it's this fact that yes, we have this nice in the real numbers we sort of have this base 10. We have this base 10 expansion, but it's not unique, right? If you choose to represent a real number in its base 10 expansion, it's not unique. However, if you choose to represent a p-adic number in its base p expansion, it actually is unique. So there's a unique way to write every p-adic number in its base p expansion. Yeah. Yeah. So how I don't know, how are people feeling? Are people wanting? I could yap about. I don't know. Maybe it's already been too long to try and break into representations of GLN-QP, but we could talk about that or the Adels, or I don't know. Maybe this is a point to wrap up. I don't know.
Maybe a part 2.
Yeah, I'd definitely be happy to do a part 2. Yeah. And
GLN QP sounds interesting.
What's that?
GLN-QP sounds like an interesting topic for part 2 or part of a part 2.
Sure. Yeah. Well, yeah. So maybe then I'll plan that for a part 2. And of course, if anyone has questions in the meantime, or I don't know, maybe you go off and you start reading other things about the p-adic numbers. And if you have suggestions, feel free to just message me and be like, hey, you know what? Actually, this is I found this, and this thing seems interesting. But yeah, maybe otherwise I'll talk. I'll plan sometime in the near future to talk about GLN-QP, which is closer to my research. Stuff about representation theory of GLN-QP. So I can also do it on short notice in case there's another week where we're short of talks or something. Yeah.
Cool.
Yeah.
That would be awesome. Thank you.
Yeah. I guess that's it. Well, thanks everyone for joining me. And yeah, I guess
thanks a ton for the talk.
Yeah, no worries. Yeah, I guess I'll talk to y'all soon.
Yeah, I think we have another one in 2 days. Is that right?
1 day.
1 day. Okay. See you guys tomorrow.
Yeah, he's tomorrow and I'm on Monday.
See ya.
Cool.
All right, stopping recording.
All right. Bye.
Bye.
I was making a backup recording, so.
Nice. Yeah, thank you.
Yeah, I'll send it over.
I'll let you know whether or not mine came out well. Yeah, I'll message you in a moment.
Yeah, sorry for throwing you off at the beginning.
No worries. You're good. Okay, bye-bye.
Bye-bye.
Bye.